The inverse square law, light intensity. This is part of the Year 11 Physics module, Waves and Thermodynamics. The concept of the inverse square law is very ubiquitous in physics. It pops up everywhere. It pops up in things like gravitation, Newton's law of universal gravitation. That's a Year 12 concept. It talks about how gravity falls off as distance squared. There's also the inverse square law used in electrostatics, so Coulomb's law, which describes the electric forces falling off as distance squared. And there's also the application for light intensity. And this is very important as well in areas like astrophysics. It's used all the time. So I'm going to begin with a source of light, a sphere. So this is how you draw a sphere in 2 dimensions. So it's a circle with 2 curves. So this is a sphere. So this is a source of light. And let's call S, capital S, the source power. Okay, measured in watts, capital W for watts. Power is measured in watts. This is the total energy emitted per unit time. So per time. Now, if you remember back to module 2, the formula for power P was energy over time. Okay, that's where we get this from. So this is the total energy per unit time, per amount of time emitted by this source, this sphere, in all directions. Now, we need to sort of think outside the box here and think in terms of 3 dimensions. So any sphere, like a star like the sun, emits light in like concentric spheres moving out away from the source itself, the star. So light moves out away in spheres. Now the intensity, so let's imagine that you're on the surface of the star. So at the surface here, the intensity I, capital I, is given as follows. It's equal to capital S divided by 4 pi r squared. Now, S is the power. Power is in watts. That's the numerator, the denominator. So it turns out that the intensity of light is inversely, so the intensity of light is directly proportional to, this is the symbol for directly proportional to, it's like a bit of like a fish. Intensity is directly proportional to power. The more power coming out of the star, the more intensity is, the brighter it is, in other words. And it's inversely, the intensity is inversely proportional to 1 over r squared, 1 over distance squared. Now in this case, so r is the radius of the sphere. Okay, it's the distance in this case. This is an inverse relationship here. So at the surface of the star, of the source in this case, the intensity is equal to the power over the surface area of the star. And the units for the denominator is meters squared. So therefore intensity has units of watts per meter squared. Now where did I get this relationship from? Well, by definition, the intensity of a wave, the intensity of light in this case, is defined as the power per unit area. So the power is here, unit area is this surface area of a sphere. Now what happens as we move away from the source? Here's what happens. So let's imagine the same source there. Let's bring it down here. Let's have an area here and another area here. I'm drawing them in different sizes for a couple of reasons. I'll explain why in a sec. Let's try and relate the intensity of light at 2 different distances from the same point source. So here's the point source here. Now let's suppose at a distance of r sub 1, the intensity is I sub 1. And the distance to, so from the set point source to area 2, distance is r sub 2 and the intensity is I sub 2. Okay, so picture these sheets. So you're looking side on and where R1 is, that's where you hit the sheet here, the surface. Same thing with the second surface. So A1 is area 1, A2 is area 2. The intensity, I sub 1 is just given by S divided by 4 pi R sub 1 squared. And I sub 2 similarly is S over 4 pi R sub 2 squared. Now let's compare the two intensities. And since, so I1, I should say, let's rearrange this here. So S is just, I should say S on 4 pi is just I sub 1 R sub 1 squared. And similarly, S on 4 pi once again from this is just I sub 2 R sub 2 squared. Because these two expressions are pretty much the same in terms of being equal to S over 4 pi, we can equate them. And this here is your inverse square law for light. That's it. In class, I didn't really derive it like this. I sort of jumped between lines, but here is a bit more detailed approach to deriving it, where it comes from. And so let's see how this works. Let's do some examples. So example 1. Okay, suppose a light source, assuming it's spherical, produces an intensity of 4 watts per meter squared at a distance of 2 meters. What's the intensity at 4 meters? Let's work this out. So what do we know? The first thing is we need to figure out what we know. Now, typically by convention, the first numbers you come across, so in this case, the intensity, we're going to call this I sub 1 in the question. And the distance, the intensity at this distance is R sub 1. And we're given, so we need to work out I sub 2 therefore, and hence this here is R sub 2. So we need the following expression, which is I sub 1, R sub 1 squared, it's like a tongue twister, this formula, is equal to I sub 2, R sub 2 squared. And it's just simply plug and play. So I sub 1 is 4, R sub 1 squared, so that's 2 squared. And that's equal to I sub 2, which is the unknown, and R sub 2 squared is 4 squared. It's just algebra in this case. Rearranging, so I sub 2 is simply 1 watt per meter squared. Let's do a more complex one. This will get you thinking a bit. This will be the last example. Okay, suppose a radiation source emits uniformly in all directions. Now, a sensor of area, this is a light sensor in this case, 0.5 meters squared receives 1 joule of energy per second at 5 meters from the source. Okay, how much energy would a sensor of area 2 meters squared receive per second at 10 meters? So this is very lengthy, but let's dissect this bit by bit. What do we need to work with now? We need to first convert what we have to intensity as follows. We're not given intensity, okay? So intensity, I sub 1, okay, for the first sensor. We're given 0.5 meters squared, and we're given 1 joule of energy per second. So 1 joule of energy per second, by definition, that's 1 watt. So the intensity, if you recall, is power over area. So power sub 1, area sub 1, okay, for the first sensor. So power sub 1 is 1 watt. divided by area 1, which is 0.5 meters squared. And that gives you 2 watts per meter squared. Now we can use the inverse square law, because we're given intensity of at the first sensor and the distance to the first sensor squared, and we're given the distance to the second sensor. So let's now use I sub 1 R sub 1 squared is equal to I sub 2 R sub 2 squared. So I sub 1 is just 2. We calculated that previously. 2 times R sub 1 squared is 5. Okay, from the source, so this is the first distance here. That's popping up in the question, so times 5 squared, I should say. It's equal to I sub 2, that's the unknown. And the distance to the second sensor is 10 meters times 10 squared. Rearranging, you'll find that I sub 2 is half a watt per meter squared. Now it asks, how much energy would a sensor of area 2 meters squared receive per second? In other words, we need the power. By definition, that's power. Power is the amount of energy per unit time, in this case per second. So we need power. So step 1 was calculating the intensity at 1. Step 2 was finding the intensity at 2. Step 3 is now to find the power. Now rearranging this, I equals P over A. We find that the power received by the second sensor, sub 2, is equal to the intensity at the second sensor times the area of the second sensor. Okay, just rearranging this formula here. Now the intensity of the second sensor at the second sensor is 0.5, calculated that here. And the area of the second sensor is 2 meters squared, so times 2. So a half times 2, and that's 1 watt of power. This is like a band 6 question, I'd say. Okay, a lot of thinking involved. It's not hard, just a bit of thinking, working with what you have, and arriving at the answer in the end. Now, just a note before I leave you to it. If you recall, intensity is proportional to 1 over r squared. This means that if you double the distance, so if this here in the denominator approaches 2r, the intensity drops by a factor of 2 squared, which is 4. In other words, so since the denominator is 4, the intensity falls or becomes a quarter of the original intensity. Okay, I'll repeat that. Denominator, if that doubles, the distance doubles. So 1 over 2 squared, let's say. 1 over 2 squared is 1 over 4, 1 quarter. So the intensity is reduced by a quarter. Also, if the intensity, let's say the distance was tripled, you get 1 over 3 squared. That's 1 over 9. So the new intensity is 1/9 of the original intensity. So just watch out for that. And that is the inverse square law for light.